Alright guys, it's your boy Chill here. Welcome back to C++ Multithreading. In the last video, I did a whole bunch of John. I see this beautiful diagram here that I made for you, which makes everything super clear about what we're going to do. But yeah, now we're actually going to code up our worker thread system. It's going to be very, very sexy. I'm hyping this up a lot, but I am confident that you guys are going to like this. And this is actually an interesting way. It shows the usefulness, the power of the modeling ability of object-oriented programming, the ability to encapsulate these complicated mechanisms and provide a very simple interface into them. So we're going to create a class. This is going to be our worker. So each one of our worker threads, we're going to create one of these objects for each one. We got some public data and some private data. So what kinds of data do we need? Well, I mean, it's all in the diagram here. Pointer to master, the condition variable, and mutex to span everything. So that's the stuff that we're going to put in here. So we need a class, master control, and this is going to be, we'll create one of these in our main function here. And that is going to be what the workers are going to call back into to notify that they're done. So I'll leave it empty for now. We'll add stuff to it later on. But yeah, master, control, master. Yes. Okay, so we need std j thread. So the worker object will encapsulate the thread that is actually running the worker, and it will manage it. So we can manage it all by creating the worker that will start the thread at the same time. So everything will just be automatic and beautiful. Std condition variable. Let's call it CV. Std mutex mtx. You always need a mutex with a condition variable. I cannot stress that enough. And now we have the shared memory, which is going to be std span int input std. No, we need int pointer to p output, and we'll set that initially equal to null pointer. When the worker is sleeping and it has no work, this will be equal to null, and the span should also be empty. So that's one thing that we can check to tell whether we have received work or not. We'll be using that. And bool dying is equal to false. This is the flag that we will set when we want the worker to terminate. All right, so that's all of the memory I believe that we'll need for the worker. All right, now here's the trick. So when we create a worker, it needs to know one thing, which is where is the master. So we will initialize master with this one. And we also want to initialize, we want to start our thread when we construct our worker. Why are you, oh, okay, you're angry because things are broken. That's fine. So to do this, we actually need, oh, what happened? Don't do that. We need a function, a body that the thread will run on. Before we just launched the thread, it executed this. But now threads have to do more than just process dataset, right? They've got to have they have to have this loop where they wait on the condition variable, and when they wake up, they check the condition, and then they do the work, and then they have to signal back to the master. So there's a whole ballet that happens, and that needs to be going into the thread kernel, if you want to call it. I don't know what you call it. Void. So we'll do run. We'll put an underscore after that to just hammer home the fact that it's private. Now, how is this going to work? Well, remember, I told you that, and you have to, when you wait on a condition variable, you have to pass it a locked mutex, and then it will unlock that mutex and lock it automatically when you wake up again. So if we look at condition variable, if we look at like wait, it takes a mutex, and it also optionally takes a predicate. We'll be using this as well. So we need a mutex, and it has to be a mutex that can be locked and unlocked. So it can't be a lock guard. It has to be something like a unique lock. So we'll create a unique lock, and it will lock the mutex. So the first thing that happens when we enter run is we acquire the mutex. We make sure that we're the only ones allowed to access the shared memory. And then we're just going to loop forever because we want to process, however many, we don't know how many data sets jobs we'll have to process. So we'll just do an infinite loop here. And first thing we'll do is we're going to wait. We're going to wait for some data, for a job to come in. So what is the condition? What is the condition that we check to see do we have work or not? So the predicate is just a function, and it returns true if you should wake up. That's the condition. That's the condition part of the condition variable. So what is the condition? Well, the condition is, there's actually two conditions. So one is p output is not equal to null pointer. If p output is not null, that means that someone has set a job on us, someone has set us up the bomb, and we got to get to work. What's the other condition? Well, dying is true. If dying is true, someone told us to die, and so we should die. So these are the two reasons why we should wake up. You might be wondering, why do we have to check a condition? If we're waiting on this condition variable and someone signals us, obviously they wanted us to do something, so we should just wake up. Why do we have to check? The answer is weird, like so many things in condition variable. But basically, it is technically possible. It is technically possible for something called a spurious wake up to happen. And so it's when the thread wakes up, but it wasn't signaled. It just wakes up for some reason. It's just like when in the middle of the night you wake up. Maybe you got to pee or something. I don't know. But sometimes you just wake up. Your brain's like, time to wake up. It's 3 a.m. Time to wake up. And so you got to check in the case of sleeping, you would check the alarm and you'd say, oh, it's 3 a.m. What the hell? And you go back to sleep. In this case, you check your conditions. And this is also good because it will check this before it goes to sleep as well. So in case this was already set, you won't go to sleep waiting for a signal that never comes because it already happened. If it happened to be set, you will just wake up immediately, or you won't go to sleep. It's just a pass through. So we wait on our condition. Then once we're awake, okay, there were two conditions. So let's see which one. Are we dying? If so, we're going to break out of this infinite loop, and then we will exit. If we're not dying, then we must have some work. So now we call process dataset, and we call it with the span, and we call it with, p output, dereferenced because this function takes as a reference. And when we're done that means we're done our work. So we should set p output equal to null pointer. And remember, when you wake up, you automatically reacquire the lock. Going to sleep releases it. When you wake up, you reacquire that mutex. So it's locked. So the mutex remains locked while we're processing the data set. And that's fine because there's one mutex per worker. So it's not like they're going to be stepping on each other's feet. And we're still holding the mutex when we modify this shared memory, which is, important. So we'll also zero out the input. And then we're done. No, we're not done, because the last thing we have to do, very important, is we have to tell the master, hey, we're done. So how do we do that? Well, in the master control, there's going to be some, condition variable, mutex. So you would acquire the mutex, and then you would signal the condition variable. You would you would increment, what do we have here? Yeah, you're going to have a worker done count. You're going to increment the done count. And then if they're all done, then you would signal the condition variable. But we are going to practice, because we're not scrub level programmers, we're going to practice some encapsulation, meaning that the worker is not going to be messing around with the details of master control's synchronization primitives. No, it's just going to call a very simple function that's easy to understand. Void signal done. And this function is the one that is going to do the dirty work, but we'll implement it later. We don't have to implement it now. I just want to make it existing so that my IntelliSense will not get angry at me. So now we do pmaster signal done. And then we're done. Once we're done our work, we go back up to here and we wait on the condition variable. And it will wait on this condition. It's not null pointer because we cleared that pointer. So it'll be sleeping until we get another job. And that's it. That is, oh wait, that's not it, because now we have to implement, okay, so the thing that I was talking about. We have to actually initialize our thread. So thread is going to be, and this is an interesting thing, if you want a thread to run a member function, pass a pointer to the member function, which is worker run. You got to put an ampersand in front of that. And you pass it pointer to the instance you want to run that member function on. If it is, a non-static member function. And there you go. And we got this function is private. No one from the outside world can call it because they shouldn't. They should only be run by the thread that is owned by this worker. And there you go. Bob's your uncle. That's beautiful. Now, our main thread has to interface with the worker in two ways, symbolized by these two little lollipops here. One is it's got to be able to set work. The other has got to be able to tell that bad boy it's time to go to the big sleep. So, set job, void set job. And that is going to be std span int data int pointer to p out. So whenever you're working with the shared memory, whenever you're accessing it, and this function is going to be called not by the worker itself, but by the outside, by the main thread. So the first thing you do is you lock. We use the lock guard here. You lock the mutex. You make sure, hey, I'm the only one accessing this right now. So we're going to set the input equal to the data. That's just assigning the span. And the output is equal to p out here. And there you go. So we've modified the data. Now we release the lock. And we notify the condition variable so that this bad boy is going to wake up, check his condition, process the data set. And there you go. There's set job. Very simple interface. The outside world doesn't see any of this garbage. It just sees, set a job, and then there you go. And now, time to kill. Void kill. So again, we are going to basically just copy pasta this. We're going to acquire the mutex. Dying is equal to true, and then notify. And there you go. There is your kill function. So here's our worker all implemented. This is all you need, probably, unless I forgot something. Go to the master. So the master is not going to encapsulate a thread because the master is essentially, that is the main thread that is, created when you launch your process. So we don't need that in there, but we do need a std condition variable. That's what the workers use to signal that they're done. And we need a mutex, always with the condition variable. I'm going to say this every time I type it because it is an important fact to hammer home. And the master here is actually going to, this control block, the master control, is going to hold the unique lock in mutex that is used with the condition variable. That is how we're going to live our life. And then the shared memory, so the int worker count, we'll set this when we create the master control. And shared memory, we have done count, which should initially be 0 because no one has done any work yet when we construct master control. All right. So now, master control int worker count. So we want to set our lock to be managing the mutex, and it will initially hold that mutex. We'll lock it. So when we construct master control, our main thread will acquire this mutex. It's good to know. And then the worker count, that's not right. Worker count is going to be equal to the worker count that we pass in to the constructor. And there you go. And that's done. Okay, so now we just got to implement the logic. So signal done. So this is called from a worker. So when a worker calls this, the worker wants to acquire the mutex. So this implies that when a worker calls this, master should be sleeping. Because if they're not sleeping, if the master's awake, the master will have the mutex, and then the worker will have to block. Mutex. Is that fine? Yeah, you like that. And then we're just going to increment the done count. And that's it. That's all we're going to do under the mutex. We modify the shared memory under the mutex. Now, after we've modified that shared memory, let's do a little check. Let's check the done count that we have there. Is that equal to the worker count? Which never changes throughout the lifetime of the program, by the way. And so we don't really have to worry about, accessing this under a mutex. If it is, then we notify the condition variable of the master that it's time to wake up because all the jobs are done. There you go. If it's not, then we don't notify him. We're not going to notify him every time we finish work because other work might still be remaining. We could, but why? Why would you want to? Now, the other function is the function that our master thread will call when it wants to wait for all the work to be done. So wait for all done. And all that does is going to be cv.wait lock this return done count equal to worker count. There you go. It's just the same condition that was checked here for signaling. But by not signaling every single time, it's probably like a slight optimization. No biggie, but... And once we wake up, when all is done, we want to reset that done count. And there you go. That's it. That's the master. That's the worker. That's the master. And all that machinery is encapsulated with just very simple interfaces. 2 function calls on the worker, 1 function call on the master, and no, two on the master as well. And everything, and Bob is your uncle, as I'm wont to say. Okay, so now let's actually modify our core logic here to account for these changes. So value sum, chili timer. Okay, so let's do quickly, because this value is used in a bunch of different places. Const expr size t worker count is equal to 4. So we got 4 workers. Okay, now we create the master control. mctr ctrl, and we tell it how many workers there are going to be. Worker count. All right, very nice. Now we are going to create the worker pointers. So vector std unique pointer. And unique pointer, I think, is an important part of this equation, because when we call, where is it? Here it is. So when we initialize our thread, we pass it a pointer to this object. If this object is just an object raw in the vector, then, vectors reallocate. They copy things to new addresses. And this thread will now be pointing, it'll be dangling, basically. So you don't want that. You want your workers to definitely have a stable address in memory, which means we want them allocated with their own allocation on the heap. So vector, unique pointer, worker pointers. So we create those bad boys. And then, all right, and then we go for size t I is equal to 0, as long as I is less than worker count I plus plus. And so for each of our worker count, we are going to do worker pointers dot push back std make unique worker, pass it pointer to the master control. There you go. This is going to create our workers, and when we create them, they're all going to start their threads, and they're all going to be idling, waiting for work, waiting for jobs. Beautiful, beautiful. Now, now we enter our actual loop here. Now we're not going to be pushing back threads. What are we going to be doing? We're going to be calling set job for each of our workers. So worker pointers at j pointer to set job, and now we pass it the data, which is our span, which is this, and we pass it a pointer to where it should output to, which is the address of this. And there you go. Now we can get rid of this. That's cleaner. Yeah, set job, and here is your job. Why did you put a space there? All right, and now when we're done, we're not going to clear out all the workers every iteration. We want to keep them around. But what we will do is we will do mctrl, master control, and we're going to wait for all done. So we signal each of the 4 workers. We say, here's your jobs. And then we wait on our master control for all done. And when the workers are done their jobs, they will signal via the master control. And then this guy will wake up and he will do another pass, another iteration of the data. And then we're done. And when we're about to die, what we should do, we shouldn't leave those threads just dangling, waiting forever. We should terminate them and wait for them to die before we leave our main thread. So for each of the workers, call worker kill, and then call, we could call worker pointers dot clear, and then that would call the destructor of each worker, which would call the destructor of jthread, which would join. So here, this would join until all of them have actually exited before continuing. But RAII, when we go out of scope, all the vector elements will be destructed anyways, so that's just pointless. But we should actually tell all the worker threads that they should be, preparing to exit. And then when we hit here, we're going to wait for them to all actually finish before we finish. And then that's beautiful. That's a beautiful thing. All right, I think I've got everything here. Let's build this. Let's try it out. So before we were getting 2.5 seconds, we would expect better than 2.5. Somewhere between 1.1 and 2.5. And it took 1.1. It took 1.1 seconds and we get the correct result. So you can see that there was no problem with breaking up the data set into, multiple pieces in terms of like extra work in looping or whatever. The only problem was that we were creating a buttload of threads. And that's not good. So if you got to do something like that, you want to keep those workers alive and you want to throw them jobs in flight. And it takes more work to do that for sure. This is way more code than when we just, this, right? All this compared to this, which fits on one screen. But as you can see, if you've got to break it up into smaller pieces, it's worth it. We just increased our, speed by 2.5x. Not bad. Not bad at all. That's going to about do it for this video. Hope you enjoyed it. In the next one, I don't know what I'm going to be doing, but I'll probably be expanding on this idea even more, fleshing it out. But until then, thanks for watching. Hope you enjoyed. If you did, click the like button. Helps a lot. And I will see you sometime in the future, probably not soon, with some more C++ multithreading. Bye-bye.